discussion with you. One is the homework is going back. The other is the test date. As you know, I'll put a simple calendar on the board here. Tuesday, Thursday, maybe I'll put Wednesday and Monday and Friday, so it looks kind of like a calendar. What is today, the 18th? So today's the 18th. If I add 7, I get 25. So the test is scheduled here for the 25. I mentioned this to you last time to think about it because, let's see, is it the 25th? Yeah. We're scheduled for the 25th, which means to really get this material in, we would have to just rush really, really fast and fly. And I don't think that makes the best learning environment, and I'm thinking you agree, but I'm going to ask you. My thoughts were to bump it one more week to the Tuesday. So if I add 5, that's a 30. But many of you pointed out that there's a lot of math tests going on Tuesday, Monday, Tuesday, I think is what you guys said. So then, May comes along and somebody suggested, and I thought that was a great idea, is maybe we do the 2nd, because the 2nd then would give us that more time, and we would just move to the next unit, which would be chapter 39 on modern physics. On this day, we would finish up our optics here, and we would have the test here. And so my thoughts are, again, to ask you any questions. Anybody want to add to this at all? Yeah?
How does this affect the half test?
Well, the next unit, modern physics, would begin on the 30th, really no matter what we do.
Right.
Because if we take the test here, we'll begin it on the 30th. If we take the test here, I guess we begin there. We finish up our optics. But how does this affect it? Oh, I guess it doesn't. I mean, what we're going to do is keep going and do modern physics, and we'll do 2.5 chapters. And then that last day of class, somewhere down here, is May, would be the test on the modern physics, which is the 3-question test, a half test. Yeah, yeah.
Is this going to be like a vote situation, or?
Yes, it is. It is here in just a second here. So, anyways, I thought this was a great idea. It sounds like nobody else has anything to add. Is that a good idea, you guys think? Okay, and I'll start in reverse order because I'm kind of leaning this way, unless, of course, there's a bunch of math tests or chemistry tests or something here, too. But who likes this idea, having the test on May 2? Oh, yeah, by far, most of you. Who thinks this May 2 is a really bad idea? Okay, yes. So if nobody thinks it's a bad idea, how about we go, I'll just do an executive. 25th? Who wants it on the 25th? Yeah.
Today.
All right.
Write an essay about optics.
There we go. So, what's real important, though, is that we make this decision, because then your review is that weekend before. Oh, and you know what? Now that we've got a little bit of leeway, maybe I shouldn't say Sunday. It could be Saturday. So let me talk with Don then about the Saturday versus the Sunday issue and see what, and maybe you guys can talk to him too and give him some feedback, what works better. I don't know what works better, the Saturdays or the Sundays. Yeah, we'll talk to him about, well, I know he never really likes to do it the day before. People need time to learn what they don't know, so that they have 2 days at the minimum. And he's always liked to do the 2 days. And so there's been a lot of times in the past where he has done Tuesday evening. So if you wanted to talk to him about that. But I think he's kind of hasn't done that in recent years or semesters, because there's so many different math classes now in the evening. And I don't know, isn't there an evening Tuesday math class? Yeah, and so that's why it kind of blocks those people out, where nobody has a math class on Sunday afternoon. So, although the world's changing, There was only a few evening classes when I was a student, and now it's everything's evening, and there was like no weekend ones. Now there's a few weekend ones. Yeah, you know, like an all-day Saturday. Yeah. My first teaching gig, I did a math, algebra 2, Saturday morning, 8 a.m. I thought, oh, wow, who's going to show up Saturday morning at 8 a.m.? But you know, that was actually some of the most prompt students I've had, I guess, because most of them were working professionals, you know, and they needed that class. They were going on it. They were used to getting at work at 8. They had no problem getting there Saturday.
Indicator for what students would be like the rest of the time.
Yeah. But no, it was. I remember a friend of mine talked me into it. He goes, "Hey, you would be good teaching an algebra." Oh no! I don't want to teach an algebra class. Oh yeah, it's on Saturday. Oh no, I was working on my thesis. Oh no, I'm too busy. Oh, but it's on Saturday. Come on. Who knew 25 years later I'd be here teaching? All right, but that's what came out of it. All right, so May 2nd, then we'll schedule the exam.
Working on your thesis while you're teaching?
Yeah. You can start. You can teach at community college once you get your master's. So there's about a 4-year period between after your master's and before your PhD. Well, and that's hard to define. PhD is a very broad time. It depends how much effort you can spend into it. If you're working full time, it could be a long time between master's and PhD. In my case, I was working enough to survive, but I wanted to, stay focused on schooling. Yeah. And that's how I eventually got talked into teaching that math class, because it's like, well, don't you want to eat? Yeah, I guess I kind of do. Maybe I'll teach you. So, all right. All right. Well, all right. Where were we? Well, let me start up the computer here. Let me remind you of where we left off on Tuesday. We had just started into chapter 37. We had put a little animation up on the screen. I'll change it. We had that flash animation from our website. But let me change it to this picture. And in fact, let me just go back and turn on the laser here. Laser. Uh-oh. Oh. Didn't get the table plugged in. That would help. All right. Laser. And if you remember, we left off shining this laser beam through a double slit with the idea, and maybe I'll power down the lights here real quick, but just to remind you, here's what we saw. Over here on the screen, we saw what we're going to call a fringe pattern. It looks like I don't have it very symmetric. It's not even there. Maybe right about there. But what I wanted you to see is then straight down the middle we get a bright spot, then we get a dark spot, then we get a bright spot, then we get a dark spot, and the fancy word is a fringe pattern. And here was the argument, just to summarize what we left off on Tuesday, was if you kind of think about down the middle of the screen, what we would call theta equals to 0. The light coming from one hole, slit I should say, and the light coming from the other slit, coming to here, travel the same distance, and therefore will have the same number of waves. However many that is. I roughly did a number and said, okay, there's roughly 2 million wavelengths in 1 meter. At least there is when you're at 500 nanometers. This is red, so this is a little, not quite 500. But if we went, and this looks like I'm a little further today, but we had about 4 meters, I said last time, and so that's 8 million. And I wanted to point out it was just a big number. The big number is not what's important. What's important is it's the same number. Because the question here is, when these two sources of light get there, will those two waves add up constructively or destructively? Depends on the relationship of those waves, which then depends on the distance they travel, or the relative distance that they travel. So forgetting about the whole distance they travel, that's not important. What is important is the path difference between them. And so down the middle, we would say they go the same distance. And so at any instant in time, there may be a crest hitting here, but a crest would be hitting there also at that instant in time. Now, maybe another instant in time, a trough would be hitting here from here. That's fine, because a trough from here would hit there at that same time. And so we would say that they are in phase. And so we need to go all the way back, and it's probably a good time. You're going to see that this unit and the next modern physics unit, we get a lot of wave stuff again. And so we got to go all the way back to the beginning of this semester, where we started in chapters, well, we started in 15, but the waves really began in 16. So that 16, 17, and 18, and all the properties, particularly 18, where we got into superpositioning, we got to bring that back up and say what happens when we have multiple waves hitting. And in this case, we would have constructive. So, not a surprise, we hopefully see right down in the center, there's the center one right there, bright light. We've got these two waves adding up constructively. But if you move up on the screen, which in this picture, you can hopefully see that this bottom one is traveling a greater distance than this top one. And if you call D the distance between those two slits, then what we get is a little triangle here. And that is the extra distance. So again, not worrying about what is the total distance to the screen. It is the part that is different that is relevant. So I'll add to that picture here. Maybe I'll do this. Here's my double slit. Here is the screen. Here is this dotted line down the center. And I am going to be looking at some position Y on the screen so that the light from the top hole slit and light from the bottom slit hits if the distance between the slits is labeled as a D. Then when I make a triangle out of this, I'm hoping you can see, and the little symbol we used last time was the Greek letter delta. It's not really shown here in your book's picture. But that Greek letter delta is the path difference. How much further does this one travel compared to that one? And as you look at the geometry, you will see that if you call this angle theta, which would be the same as this angle theta, oh well, I should probably do a little bit better. It's the same as this angle theta. So in other words, the angle on the screen being the same as the angle of this little triangle that's formed here. But that distance would be d sine theta. Of course, that's just your regular trigonometry, so hopefully that doesn't surprise you. But here's what's interesting. What if d sine theta is an integer number of wavelengths, either 0, 1, 2, 3, compared to what if d sine theta is an integer and a half? Well, I'll start back to here just as our review. What if this is an integer number of wavelengths? What is going to happen? Yeah, you're going to get constructive. We call these maximum points, meaning it is bright. And the reason it's bright is because the waves are in phase. And so if this extra distance happens to be one wave, then what will happen over here at this point on the screen is that a crest from this one would line up with the crest of that one. Now, granted, it would be one more wave. And so instead of having just 8 million in the bottom one, well, let's say we have 8 million in the top one, this bottom one we have 8 million in one. One more wavelength. So again, it's not the total number. What's important is the difference between the two. And that's what this symbol delta is going to be. In fact, do you want to know the answers to all the problems for this chapter? It's right here. Look at the path difference. Look at how the two waves come together. Or 3 or 4 or infinite number of waves come together. Right? This chapter is on the interference. The whole chapter is saying what happens when we have multiple waves. We're starting here with 2 waves. And just asking, you bring them together. The question is, do you have constructive or do you have destructive? Or do you have something kind of partway in between? Which is what we're going to expand on today. And of course, there is right in the center constructive. And then as you move away from center, it gets less constructive. But it still adds up pretty good. So you can see that there's a width to the brightness. And then it tapers off and goes dark, and then it tapers up to get bright again. So there's right in the center of those little round dots is the bright spot, but slightly to the left and the right, we just don't have complete constructive interference. But we're far from destructive interference, so we do see a width to it. So more coming up. Right now we are just looking at there would be bright, dark pattern that would continue.
Are there 2 slits in there?
Yeah. 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 And they're really close together. So you're looking at it going, I don't see 2 slits. But yeah, there are. Yeah. Yeah. And of course the other part of this, again where we left off, and I thought I better review today because although I joke with you, I'm really serious. The answer to everything I'm going to do for the rest of today is look at the path difference between these 2 waves. See how the relationship of the 2 waves add together. See if it's constructive or destructive or maybe partly in between. And that will explain what is happening. And so the whole chapter is, as the title says, about wave interference. Take 2 or more waves and combine them together and see how they add up. Are they in phase? Are they out of phase? Are they something in between? And so we left off with this, the first and the simplest explanation. It's called the Young's double slit. You shine the light in there. You look at what comes out onto the screen. You get a pattern. It's very easily explained in terms of waves. It's an excellent experiment to show the wave nature of light. And so when this path difference is, say, 1.5 wavelengths, then a crest and trough would line up and you would get destructive interference. And so if I would come back to my little screen here, I would say, okay, this point right here, the same number of waves going back to one opening and the same number of waves going back to the other. And as I move to my right, it gets dark. So right there, it is 1/2 a wavelength further back to one opening compared to the other. And as I go even further over, then it is a whole wavelength further back from one and compared to the other. And so I think you got that idea. And so that was our, like as I said, our double slit experiment. Because let me ask you this. If this makes sense to you, let's mix it up a bit. What if I change D? I'm shining this laser beam onto that screen. They separate out. If I were to say, what is the angle, let's say, between the center one and the first, m equal 1? All right, so I'm going to look at bright spots. And I say, all right, let's look at sine theta. I would say, well, sine theta must be, well, I'll write it as m lambda over d first. But if I'm looking at the first one, what is the value of m? 1. All right, so that's just a lambda over d. Fair enough? In fact, maybe I'll even take it one step further. Let's not talk about the angle because it's really hard in this experiment to see the angle. You can see distance, can't you? So let's do this. Let's add to this and say, let's look at tangent of theta for a moment. If we call L the length to the screen. And y, the distance up, or in this case, right on the screen. What is tangent of theta? Y over L? Now, I claim that this is another good example of using a small angle. Remember we said you could approximate sine theta or tangent theta with the angle theta if you're looking at small angles and you're doing it in radians? And so let's try that. We've done it already quite a few times this semester. I can say sine theta is approximately equal to tangent theta, which is approximately equal to theta, if we're going to measure things in radians. If we're willing to say, let theta be somewhere greater than 0, but less than 0.5 radians, which is about 30 degrees. So again, if we're willing to look at angles, say less than 30 degrees, isn't that about true? Now look at my experiment. Would you say that angle's less than 30 degrees? Extremely less than 30 degrees, right? I mean, there's not much spread here. So I'm going to take this small approximation and do the following. I am going to then replace this sine theta with tangent theta, which really is y over L. And so whether I ask you to solve it for theta, or I think maybe more appropriate for the way I have it set up here, is to solve it for what is the distance on the screen, let me ask you again. As I shine this up here, how far over is the first bright spot from the center one depends on what factors? Well, I think you can see it here. It depends on what order I'm looking at. So we'll call this the order. So I'm looking at the first one, m. How far is the first one, m equal to 1? How far on the screen? What does it depend on? The wavelength, the distance to the screen, and the distance between the slits. I think the easiest one is the length to the screen. I mean, you could imagine, what do you think if I would move this cart a little bit closer so L gets smaller? Yeah, they get a little closer together there. And I don't even know if that was enough that you could even notice it. But as I get closer, I mean, obviously these things are spreading out. And so if the screen moves closer, then y gets smaller. Okay, that one's pretty obvious. So I won't spend much time there. But the other two, I do want to spend a little time. What happens with D? Let's say D gets smaller. What's going to happen there? It spreads out, right? In other words, the amount of spreading is really how close these are together. Now, hopefully that makes conceptual sense. If you get these two slits really close together, your first bright spot occurs when this bottom one travels an extra distance of a whole wavelength. And if they're really close together, that extra wavelength needs to be at a big angle. So, why don't I try it? These are actually pretty close together. Yeah, I'll do this one. This one. They are really close together. This one doesn't say. Bummer. This one, oh, doesn't say on it either. But I happen to know there's 600, no. Oh. There's, shoot, it must be, you're going to use it in the lab. So, but it must be a separation of whatever 1 divided by 600 is in 1 millimeter. Okay, they're really close together. And so I'm not worried about the number, but it's the concept I want you to see. Question? Yeah.
So if the how which way where the light goes, if the light goes, if those points on the little white paper are where the light constructively interfere with each other, does it mean that if you shine white light through it, we get different colors? Because the thing is, because light's kind of.
Oh, I am so glad you asked that. Because again, the rest of this chapter is the same logic again and again and again and again. And I'm going to do that one, but I'm going to start here. Let's just do one color. You're asking about multicolors, that's common. But with one color, one wavelength, distance between them, the short distance, if I put it through here, you might be pleasantly surprised. Almost too surprised. Where is the first dot? On this side, it's over here. On this side, unfortunately, it's hitting the black screen, so it's hard to see. There's m equal 1. Much bigger in y. These two dots are much closer together. M equal 2. Might have to turn off the lights for us to see it. I can see it on this door. There it is right here. Right there. From this one. And so it is just enough intensity to see it. And so over here there's 2. Here's 1. Here's 0. Here's 1. Did we find 2 then? Oh, thank you. Yes, it's for you can see it. Wherever it is, somewhere in here. There we go. Somewhere? I don't see it. All right. Somewhere up here, okay, you guys say. All right. But there is the number 2. So, again, probably not a surprise for you. In fact, what I'm going to do then is pass these out. These are what we call the cool glasses. Now, let me show you the cool glasses. The cool glasses are essentially this, right? I am going to take this, and here's the cool glasses, and maybe I'll just shine it here onto the board here. But if I were to take in this case, I'll start with a red beam, and here's my red beam, and maybe I'll turn off the lights again. And if I were to shine the laser beam through these cool glasses, actually, let's see what we get there. I'll angle it up, but you can see the spread, right? There is 0, and then 1, and then 2, and I don't think we're going to, 3 is kind of hitting this side over here, so my parts of my glasses are hitting it. But you can see it is spread out. Fair enough? I won't shine this into your eyes here, but yeah, and you don't have to put on the cool glasses yet. But I want everyone to get a pair of them. But here's what I do want you to see. What if I make this next question for you? Let me turn the chalk. Oh. I thought that was a bird. All right. All right. So hopefully changing D makes sense, that if I make it smaller, of course it spreads out more. If I make D bigger, it narrows in. Okay? It's probably why most of the time in your life you have not seen the spreading of this light, because most of our holes and our slits are, a millimeter or more apart, or even a fraction of a millimeter. That's just not small enough. These got to be really, really smaller than a millimeter to see the light spread out here. Now, what if I do a different wavelength? And that's why I got these different laser pointers here. Here I have a red laser pointer, a green laser pointer, and a, what color you want to call that? Violet. It's kind of on that transition blue to violet. Indigo.
You're colorblind because indigo is right between violet and...
Yeah, it's kind of on that border of indigo and violet. Yeah.
No, it's violet.
It's violet? No. All right. Well, it is a wavelength of...
It's indigo.
Is probably the best answer.
Yeah. 400?
Well, they give a range. They probably just mass produce them and they don't really... but it says 450 to 470. Yeah. Well, anyways, I do want you to see this. How would the spread occur for different wavelengths? Would it be the same spread for different wavelengths?
No.
Which would spread the most? The longer wavelength. So what colors would that be? Red. So if I were to take this pointer and turn off the lights here and to shine it in here, maybe I will call this the center mark. So I will shoot the laser at that mark. My red one, maybe I should even do it in red. So the red one's right about here. Fair enough? The green one, there's a green pen here. Green, where's the green one hit? All right, so I'll shine the laser pointer at the same center spot right there. And so it looks like my green one's right about there. And so as you guys correctly said, the red one would spread out more than the green one.
Because it has a higher frequency?
Well, it does have a higher frequency, but it's in terms of wavelength that I'm interested in. So I'm going to say it a different way. I would say because it has a smaller wavelength. I mean, yes, it has a higher frequency, but it's the wavelength and the fact that to get this distance to be one wavelength, and green is a smaller wavelength than red, the distance has to be less, which means the point on the screen is less. Because that's where you get your first interference, when this distance is one wavelength. And that's what you get for green. Now, before I lose it, I'll take your questions here, but let's go with the indigo. So where's the indigo blue going to be? Or the violet? And so if I shine it right there, that's indigo. All right, that's the indigo. That's right. It's on the internet. The internet doesn't lie. That's right. Yeah, where'd you hear that? On the internet? Right, you saw the commercial. Oh, meet my French model. Yeah, that's right. Okay.
Does everyone have different perception, though?
Yeah. That's why we really like to stay away from calling them colors in any way. It just, because someone's going to call it purple, somebody's going to call it indigo. Hopefully we can all run an experiment and get the same wavelength and end of story. That's the wavelength, whatever color you want to call that. Yeah, because your biologies are all slightly different. Your retinas react slightly different, just like we all have slightly different hair color or even hair. We all have slightly different effects of our retina. So what one person calls orange, another person calls red, what somebody calls indigo, somebody else calls violet. So just kind of want to stay away from the biological effects. Anyways, but that was the second or third thing I wanted to show you here is what happens when you change each of these. Okay, now, your question? We're good? All right. So now, let's continue on here. What if I were to shine, and this was your question, white light?
We'll split them into different colors.
What would white light look like on here?
Rainbow, different colors.
All right, so let's talk about it here. What would it look like down the center? Right here, this is our center. What would happen to the reds, the blues, and the greens? Wouldn't it, down the center, you get constructive interference for any wavelength? It doesn't matter what wavelength you put down the center, they're going to add up. If I shine red through here, right here, I'm going to get constructive interference for the red. But if I shine green, which has a smaller wavelength than the red, just means that I have more wavelengths in here. But as I was trying to point out, so what? That doesn't matter. Are they in phase? Yes. So you would get constructive for the green. What about the blue? Same idea. And so all of the colors would add up constructively. So what would you see straight down the center? Yeah, white. You shine white light in here, straight down the center, you're going to get white. But as you get off of center, what is this saying to you? Right, and I hope you see the rainbow effect in the sense that off to this first order here, you're going to see your different colors. The one closer, and of course it spreads out the light. like we saw it spread out for dispersion. Now it's a different reason. And I want to emphasize that. But of course, on the screen, it still looks like a rainbow. It's not dispersion, but it is still kind of that rainbow-looking thing. And so I would have, I'll just do it in the order that I'm familiar with. I would have red, the furthest away from the center. I would have orange, which I don't really have an orange pen, but I'll just put an orange there. Then I would have yellow. Then I would have green. Then I would have the blues, the indigos, and the violets, right? And so as you pointed out, I would have a rainbow color. And yeah, I will show you here, but I want to make sure you get this idea. What else would you see? This is order 1.
Another one right on difference over there.
So wouldn't you see the same thing again? Shouldn't there be another blue one which would correspond to m equal to 2? And of course you should see more green. You should see more red. And so shouldn't you see a second rainbow effect? Yeah?
Hold on. Since purple spreads out, doesn't spread out as much as the red does, I think that it doesn't mean in the same distance, over the same distance, you see more purples than you see red lines. So you probably see more purple lines than you see red lines because.
Oh, I'm so glad you asked. So I got a rainbow here. Now, did you notice how I've drawn it spread out? Do you see that in the math? Do you see that if you take the difference between, say, the blue and the red, the size of your first rainbow would look like what? Well, let's see. Delta Y, well, it would be position of the, and I don't care which one you want to do first. Maybe I'll do the red because it's further out and then subtract the shorter one. But at this value here, where m equals to 1, I would have the wavelength of red, L over D, minus the wavelength of blue, indigo, violet, whatever you want to put there. Right? Isn't that the spread of my rainbow? Now here's why I say that. Let's jump over here to m equal to 2. Now maybe this is a good time to pause. You see how I'm really doing the same thing with the wavelength? Of course, it's more complicated because I've got multiple wavelengths going through here. But now there's going to be a spread here. Yeah.
Why is it blue?
Why is what blue?
Why is the second one blue instead of violet?
Oh, okay. Sorry. I should do violet. Just because I'm lazy and they're the blues. Yeah. So the reds to the blues. But I should say deep red, blood red to violet. How's that? Right. All right. So here is the spread. What am I going to get over here for the spread? Twice as much. Exactly. And so this rainbow will be further over, twice as big. Because when I go to solve it, it's m equal to 2. And so this would be 2 times the wavelength of the deep red, L over D, minus 2 times the wavelength of the violet times L over D. Okay? And so I wanted to point that out. And hopefully you saw a lot of things. Yes, we get a rainbow. Yes, we get multiple rainbows. They're not the same size. The blues are violets are closer in. The reds are further out. The green is in the middle. It gets better on the next step. Yeah.
Could you use this method to separate frequencies of non-visible light? Like
Oh, sure.
isolate a specific radio frequency?
Oh, yeah, and you do. In fact, I think one of your homeworks is a good one where it's kind of weird. We spend the whole chapter talking about optics and these light waves, and then they go, you have 2 radio towers. What? Because the radio towers would have this same pattern, the same interference pattern. And it's great for guiding in airplanes into an airport, because if this over here is the airport and there's bad weather and it's snowy or foggy or rainy and you can't see the airport, and you're a plane coming in, if you remember that speckle pattern, bright, dark, bright, dark, bright, dark, as you just move a little bit, you'll pick up one of the strong signals. And you don't know if you're in the center one or 1, 2, or 3, but you know it heads back to the airport. And so you just follow that signal for the next couple of miles and there will be airport. And so they'll put 2 radio towers right at the runway and use the double slit and a few other things too. So, and then guide the plane in there. And the other homework problem is really weird. You know, we've talked this whole thing about optics, and you read the problem and it says you have 2 little kids making waves in a pond. And you're like, what pattern shows up on the, the edge of the pond? And you're like, kids and ponds and waterway. But it's a property of waves, and so you'll see that. They do it with radio waves, they do it with sound waves, they do it with water waves. They just throw it out there to see if you're really paying attention to what the physics is. So it's a property of waves. Did I see another question? All right, so back to here, look at order number 3. This is, I think, where it gets the most interesting. This is why I gave you the cool glasses here, is if you go ahead now and look at order 3, what are you going to see over here? Okay, another rainbow, 3 times as big. Which one is closer to the center? The violet. In fact, when you run the numbers, the blue one, and this is one of your homework problems, to ask you calculate where is the 3rd blue one and compare that to the 2nd red one. They overlap. And I'll say the calculation for the homework, but you will see a larger rainbow, but more interesting is you will see an overlap between the end of the 2nd rainbow and the beginning of the 3rd rainbow. And your eyes will pick up both a red and a green. I mean, a red and a blue, or violet. What do you call that? A magenta? No? But when your eyes pick up both of these, kind of a more of a magenta effect. And that's why I asked you to grab the cool glasses. So now that you got your cool glasses on, let's take a look at some white light.
Are there any more of those?
Yes, where? There, well, maybe I'll just give you mine here. I'm going to have to go from memory. Okay. Oh. All right, here you go. All right. But look closely at that. Can you see the rainbow? Okay. Look at order 0. Order 0 is straight at your eyes. Straight at your eyes. Doesn't it look white? And then look a little to your left or your right. What do you see? See a rainbow? See the closest one is a blue? Then it goes to a red? Then do you see a small gap? Thank you. Do you see a small gap, a small opening? Then you see the next rainbow, and of course, does anybody see this? Do you see the magenta? Yeah, and so that's the, in my case, kind of out for here, but I see the end of the 2nd rainbow overlapping in there. Okay? And we can kind of see the same thing if I do something to this effect. What's this? How does it work?
Magic.
It is an optical disc, and it's got grooves in it. It's got slits, if you will, where the light is. Well, now, it's really not designed to do what I'm going to do, but it works well. These are grooves. And I am going to shine the laser beam right here on this edge. And if I shine it on this edge, there should be straight lines. And I guess I will reflect it back, and that's kind of the I would say a difference here. This doesn't go through onto the screen. These aren't really holes. These are little grooves cut in there. So they hit the hole and then they hit the mirror behind it and come back. So it's kind of like the same idea. But if I power this down here, you will hopefully see this one here. That one. That one. Come on in here. That one. And that, what I would call order 0. That's the light coming straight back. Okay? In fact, maybe I can just arrange it so I can compare things. Let me do the straight back right on that metal pole. Oh, then it's black. Okay, how about we do that sign right there? All right. So I'll put it right on the P for persons. How's that? All right. So there's the straight back. All right. And so this is what I would call order 0. Right? Right there. Okay. And of course, depending on the distance, I would get order 1 and order 2. Order. Oh, so here's my next question. How come I don't see order 3? Or 4, or 5, or 6, or infinite. And so when we started this discussion, I think I left you with the impression that m would go forever, right? But that means the angle would have to increase forever. Isn't there going to be a maximum? I mean, can't this angle only go to 90 degrees? And I would even argue our math isn't even valid for large angles. But even if we ignore that, as we get to 90 degrees, there is going to be a limit. So when we started off by saying 0, 1, 2, 3, and 4, it's not dot, dot, dot forever. It's stop somewhere. It is dot, 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 n. There is a maximum somewhere, because you can't go more than 90 degrees. It is why when you put on those cool glasses, you saw the central, you saw order 1, you saw order 2, you saw order 3. I don't think you can see order 4. I'm not real sure on those glasses if it cuts off on 4. But I know on this CD, I can see 0, I can see 1, I can see 2, but apparently the size of those slits is enough that I can't see 3.
Isn't that how you get the information off this?
Yes, and so this is exactly what the laser beam inside your computer or your CD player, do they even exist anymore? Anybody play? Yeah, I do have a CD player too. It's right next to my tape player, which is next to my album player, right? My record player. My 8-track, yes. Which is right before my reel-to-reel, you know. So I got the Beatles on reel-to-reel, and then 8-track, and then cassette, and CD, and now iTunes, right? Okay. So, anyways, I'm getting silly on you, but the CD is exactly as you said. And that's why I wanted you to see this. It wasn't just the experiment. I wanted you to see this is how the optical players work, although they're getting less common. But what they do is you put the grooves in there, and the grooves reflect the light. And they actually use this. It's very interesting. This is the signal. And so as it shines through and it hits and reflects, that's where the data is. So that's the main thing that they want. These second ones are used as guide paths. They go down on a shiny disc, and if there's like a vibration because of the disc, because you've got it strapped and you're running, or it's in your car and you go over railroad tracks, this controls the beam and keeps it on, so it redirects the beam to keep with the optical disc and to keep track of vibrations. But I want to make a little mark here. Maybe I should do it in red, because this is where m equals 1, and this one over here is where m equals to 2. And I could even, I'm not going to, but if we wanted to know how close are these optical grooves on that disc, couldn't we calculate it? which, by the way, in a couple of weeks, that's one of the experiments you will do. Not with an optical disc, but you are asked to find the distance between two slits. We just put them up there, you shine the laser beam, and of course now you can see what you're supposed to do. You are supposed to measure where is the central maximum, where is the first maximum. If I were to measure this angle, then realizing I'm at order 1, knowing the wavelength of the laser beam, which this one is 632 nanometers, couldn't I find D? Yeah. And so I can find D. Now, we already asked this one before, but let's ask it again. What if the size between the slits, and in this case the grooves on the optical disc, changed and got smaller? Yeah. Where would be the central one? Same place. Where would be m equal 1? At a slightly bigger angle here. So, we will do a swap out. We will go from optical disc 1 to optical disc 2. We will go from a CD to a DVD. How can we get more information on a DVD compared to a CD? The grooves are closer together, right? We can fit more on here. So that means then when I take my CD and replace it with my DVD and shine, oh, I don't have the angle quite the same. Oh. All right, so I will put order 1 on the P. I think that's order 1. Yeah, I mean that central one, 0. Order 1 should be, and you may not even be able to see it, and I'll turn down the lights, but here's order 1 way over here. It's behind this crazy machine here that you may not see. But there is order 1. And of course I could do the same math. I could measure that angle. And I can measure the angle, and of course I know the wavelength, the 632 for that red laser beam. Now I'm again order 1, but I'd get a different D, and I'd get a much smaller D. And in case that would tell me some information about that optical disc. Yeah.
How is it then that they put information into that? Like how does it work? Do they?
Well, okay. So it works like this. There is a groove, a track around it, and then another one, and then another one, something like this, okay? And the laser beam fires, the central one, right there, that one, is designed to hit right there, that's where your data is going to be. And this will be shiny or dark. Shiny or dark, shiny or dark. Okay? And so as the disc spins, the laser beam will get reflection or no reflection, reflection or no reflection. And so the pattern of on, off, on, off, on, off, on, off is the optical information.
Is it just straight and on off, or is it like a gradient? Is it?
No, it's straight on off. Okay, and so when it makes a transition, that's why it's digital. All of our digital electronics, anything digital means you either have it on or it off.
Binary.
Binary, exactly.
So how do they do the multiple layers?
Okay. Hang on here, but I wanted to add to this then of course, this is not quite what I'm focusing on today. I'm focusing on the double slit, but the controlling beams are these first order. And so the order m equals to 1 is shining right there. And between the data tracks are shiny tracks. And these should reflect back to the computer should keep on board that, hey, we're getting a reflection. If there's any vibration, if this disc moves and this central beam gets off track to the left or to the right, then the guiding beam here, the m equal to 1, will get on this data track and will now start flashing on, off, on, off. Now, that would be data, but the computer at that point is not interested in the data. The computer at that point is interested to say, your beam has wiggled too far this way, and we'll adjust it back. And so this beam will hopefully stay on the data track. Well, the beam doesn't move, the disk spins, but as it spins around, hopefully it will stay on there. Okay. Now, the multiple layers, let me just say it this way, are designed so that one layer reflects blue, another one reflects red. So it's really the same thing twice. We just have 2 laser beams for our data. And it's geared towards one reflecting only red and the other one reflecting blue. And the next step we're going to get to shows us how could we do that? How could we only get reds and how can we only get blues? So I'll get to that because I know that's going to be your next question. Well, how could you get just red and blue? Well, coming. Okay? But it's an interference. And so I'll say it again. I'm not going to do anything in this next 2 hours that isn't just the same thing. Mix it up a little bit. All right? Let me mix it again here. Oh, so I thought this would be fun. Now that you saw the CD or the DVD, let's get some white light in here. I mean, I think you essentially saw it with the glasses on here, but I've got the mirror and some sunlight out here. Oh, and if I prop open the door, and get some really nice white light, sunlight in here. And I pick up my CD and I shine it back on the P for person. That's not a very good reflection. Am I hitting it well? Ah, there we go. There's that. And can you see, maybe I got to put it over here, can you see the rainbow? Bummer. Maybe I should turn this off. Maybe I should try to put it on this screen here instead. Let me find the sunlight. Sunlight, there it is. Okay? And so there is order 1. And order 2, I guess I don't really. Can you see it? Is it on me?
No, just barely to the right of it.
Just okay. In fact, maybe if I got a little closer to the screen where it'll be smaller. But again, you can see the rainbow, the violets to the red, and then second order. I don't see it. Is it over here somewhere? Oh, I keep moving. All right. And of course, got me in the eye. Okay, and if I do the DVD, you'll see the same thing. Although, you know, because the grooves are tighter together, you'll see the rainbow spread out. And this one's actually tinted. I should get a, I wonder, this one is actually tinted blue. So it's going to be hard to see the red. It doesn't really like to reflect the reds. And there's the blues. But the DVD, of course, as I was trying to point out, is closer together.
And do the Blu-ray discs have even smaller slits?
Yeah, and then the Blu-ray is, and you can kind of see the advantage here, as we get to smaller and smaller wavelengths, there's two nice advantages. One I showed you. One is that the first order gets tighter and tighter. And so you could get these grooves and control them with your guidelines better the smaller the wavelength. What I haven't explained yet, but will become apparent in the next chapter, is that also the central one can be focused smaller and smaller based on its wavelength. And so the blues focus into a smaller point than the reds. And hence, if you want to get a lot of data on a disk, you need to make your data track very narrow. And you can make it about as narrow as the wavelength. So the original ones used an infrared. Then they went to a red beam, and now they've gone to a blue beam. And now the question is, do you go to an infrared or do you do multiple layers? And they seem to be having more success with the multiple layers than they are the ultraviolet.
Stop using physical media.
Or just, yeah, it's getting, so optical medium is probably a dying thing there, so yeah.
Why are they limiting it to visible light only?
Why what?
Why are they limiting it to visible light?
Well, no, it's just the technology. How do you make a laser that is at smaller wavelengths? It gets harder and harder. So the original audio CDs, and this isn't an original, this is actually a burnable one, but the original ones was when technology got to the point that you could make a solid state laser in the infrared. So that gave you enough data on this thing to put about, what is this, about 650 megabytes? 700 megabytes? Okay, and so that's as much information as you could get.
What's the difference between MP3 CDs and the actual audio CDs?
Oh, well, that's not the amount of data that can be stored. It is it's the format and the size of the file. So an MP3 is a compacted, compressed file. So you can get a lot more songs on an MP3 disc, not because there's more information or more data that can be stored. It's that the song itself is a smaller file because.
The laser discs that were like this big, that would have been infrared.
Oh, now you might be thinking even back in the 70s, the big laser discs like this, well, maybe this. Yeah. Now those, that's a little different. Yeah, they were infrared, fair enough. But they also weren't digital, they were analog. And so your disc was this big, and I think you got like, what, a half hour of video?
Yeah, you had to flip it over.
Yeah, because you could play a whole movie. You had to put it in, and halfway through the movie, you had to pause and take out the disc and turn it over and put it back in. Yeah. So. Yeah, amazing.
Wait, is that how record players also work? Record players?
Well, they weren't optical, if that's what you mean. So no, record players weren't optical. They actually had grooves that the material actually went up and down so that a needle, as it moved across, the needle would go up and down, moving a magnet that would generate the electricity, and it would go up and down in the same pattern that it was recorded.
So
And
that's a gradient. That's not like on
yeah,
off.
and that would be an analog thing too. In fact, not Edison, or was it Edison? Who made the first recording? Thomas Edison. Yeah, Edison. And his idea was brilliant. I think. I mean, he just took a megaphone, and he took his sound waves, and so he just talked into the megaphone. The sound waves came down, and so all those pressure waves came on a little metal needle on the end, and as the sound waves hit, it would move that needle in the pattern of those sound waves. And then all he did was put that needle against a metal plate. I think it was 10, because 10 is reasonably soft. You think its first cylinder was wax? Could very well been, and maybe it was later they got to 10 ones. But as you talked, it would just poke in and out of the wax, and then the pattern would be the pattern of your voice. So then all you have to do is take it and put the needle back on there, and as you turn the cylinder, the needle would move in and out, making sound come out of the little cone. And so no electronics at all. It's kind of the same thing that you may not have realized it. Many of you probably played with this toy when you were a kid. You ever have one of those ones that's got all the animals around, and it points to a cow when you pull the handle? And it spins and it says, "This is a cow." A cow goes moo. There's no batteries, right? All it is a 10-cylinder that somebody first talked into it. So this is a cow. It goes moo. And then when you play it back, there's a needle that just moves back and forth. Imagine that, no batteries. It was 10? Oh, okay.
If you've heard that recording a few times.
I did. I'm glad my kids are past that stage. We're on to a new chapter. Yes, I've had a few parties in life, and getting rid of big plastic toys was a big one in my house. Oh, thank goodness. Another one was out of diapers. Like, yes, I've been changing diapers for 8 years. I don't have to buy any more diapers. No more changing diapers.
What about little Legos on the floor?
I still got little Legos on the floor. I'm not out of that stage. My youngest is still 12, and he loves Legos, and they're everywhere. Yeah, no, not out of that one. High chair was another party. You know, my house and my kitchen, living room are pretty small, and you put these giant plastic high chairs in there. It's like you're constantly kicking it over. Like, yes, we can get rid of high chair. Car seats. Oh, that was probably the biggest. It's no more 10 minutes getting in and out of the car. Yeah, that was a big sea change. I need a better eraser. I hate these things. All right. Anyways, now let me ask a tougher one for you. Now that all those made sense, I run the same experiment. Here's the laser beam. Shine it through the gradient. Put it on the screen. And the whole thing is done underwater. What does it look like?
It's the same. That's the same. The wavelength.
Wavelength changes as you're in water.
Right. So let's tie this back to last chapter, or I guess it's really chapter 35. But as we go back to the last chapter, then we will realize, as some of you are already saying, the wavelength will change. Right? Now, I don't think any of our logic will change, so that's the good part. I'll put the picture back on the board, but as many of you are noticing that you would go through exactly the same logic, except as we go from here to here, and we realize that this is the path difference, d sine theta. We did this before, d sine theta equals an integer number of wavelengths. What would be different underwater? Wouldn't the wavelength change? By how much? Yeah, so there's n. So this is where we're going to get our maximums. And when are we going to get our minimums?
n plus 1/2.
Right, and so no problems there, right? All right, let me mix it up some more. What if instead of 2 holes, I only have 1? And I lay a mirror flat so that the mirror is now a distance h from that opening. What will I see?
Well, it depends how big H is.
Now, let's go back to the chapter you're currently working on here, right? What do we learn about lenses and mirrors? Particularly in this case, a mirror, a flat mirror. Doesn't it create an image? And of course, that image can be thought of as the object for the next piece of our optics, right? So let me ask you, is there an image of this opening in this mirror? Yes, and where is it? Right there.
It's a virtual slit.
And so I have a virtual image, which I should probably call a virtual slit. And now I have a double slit experiment again? And so aren't I going to see fringes, bright, dark, on the screen? Because what is on the screen is essentially controlled from the light that comes. And I would say I get light directly from that opening. I also get light ricocheting off the mirror as if it came from that image. And so I would put my optics, my image in the mirror, back together with my double slit. And so I would say this is equivalent to a double slit where the distance d is twice h. Fair enough? And so if d sine theta equaled an integer number of wavelengths, and maybe I'll just put over n, because I don't know, this may be a mirror underwater. I got a single hole, I got a mirror, I got it underwater, all right, so I'll put it in. This d can be replaced now with 2h. And then other than that, it should be the same thing we've been talking about for the last hour, right? Except one more thing. You didn't miss it, right? You were just testing me to see if I missed it. Yeah. So what am I missing?
Isn't it only true if the angle of incidence with the ray hitting the mirror is only 45 degrees?
No.
We assume g sine theta when the angle of incidence were 90 degrees. Because of that line that you drew.
Okay, so this is supposed to be 90 degrees, is that what you mean?
Yeah, what is the significance of it?
Oh, and so in this picture? Oh, so in this picture, I guess there would be some other line. I'll change colors. But there would be some other line here. Right there. Yeah. And so what's the one thing I'm missing here? Oh, okay, fair enough. I am assuming it's a flat mirror. Yeah. If it wasn't a flat mirror, that would be a good question. A little beyond the scope of this class, though, so I won't go that far. But the reason why is, if it was a curved mirror down here, it would still form an image, but would the distance be the same? No. Now, that wouldn't be out of reason to ask, actually. You would just have to calculate what that new distance is, and then your d would be p plus q. So actually, that's a good one. I like that. I gotta make it a test question. Yeah, that would be a nice image. But what I am a little concerned about is not only would you have the distance between the two slits, which you could do, but the other thing you would have is the size of this second slit would be a little different than that one, because we've got the magnification effects of it. And although we haven't really talked about it, we've kind of implied, since we got constructive and destructive, that the amount of light has to be the same to get destructive interference, and so the size of the hole really has to be the same. And so there would be an added twist to it. But no, I am saying it's a flat mirror. So what else am I missing?
Oh, it's a dark spot.
Yeah, let me take you back. I guess it's chapter 16 or maybe it's 18. I'm not sure which of those waves won. But maybe you remember this. What happens to a wave that comes in and hits something solid? What did you notice? It inverted. As opposed to hitting something that is not solid. See, it doesn't invert. It stays upright. All right, so we did this with sound waves and string waves. Now, let's apply this to our light waves. What do we mean by something more solid in this case? And I would answer that by saying it goes slower. If you hit something with a higher index, you're hitting something, in a sense, is more solid. It is slowing the light down. And so if you reflect off of something more solid, and in this case we are, down here off this mirror, we're reflecting off of probably a polished aluminum. Unless it's a nice mirror, it'd be polished silver. But it would come in and bounce off of there. And as it bounces off, guess what's going to happen? this right here has a phase change. And what do we mean by phase change? Yeah, wherever there was a crest, it now becomes a trough. Okay, so now let's talk about this. When I first put this on the board, d sine theta equals to m lambda, I bet you were thinking that's where light was going to be at a maximum. But let's think about it again. Why was it a maximum there? Is because the two beams added up together. Crests lined up with crests. But if one of the waves, which in this case is the reflected beam, the crest now instantly becomes a trough, what would have been lining up crest with crest now becomes crest with trough. So it's no longer a maximum, it is a minimum. So a situation like this is, I think, a little bit harder than any of the other ones we've done. But I did want you to see, what if you change D? What if you change lambda? What if you had multiple colors? What if you did it underwater? What if you put a mirror? And next, what if you put a lens? All right? And hopefully you'll see that here. So anyways, there would be a shift. So this equation would be the equation of where you get dark spots. And so interesting enough, down the center would not be bright. Down the center would be dark. And then we would get bright, and then dark, and then bright, and then dark. And so in that sense it would be the same. You would see a fringe pattern. But 0 degrees right down the center, right here where what would turn out to be the edge of the mirror, because remember, the image distance would be the same as the object distance, okay? Then you would get minimums. And so that means d sine theta equaling m plus a half of wavelengths would be your maximums. And so they reverse roles. And so that might have caught you off guard there. Like, ooh, didn't really expect that. How about this next little piece? And I am going to grab a rag so I can erase better here. Hang on. I got the spray out here, thanks. I just needed a...
What does the n mean in that equation?
N would be the index of refraction of... yeah, the surrounding. So it would be the N of what the light is traveling through. Because I want to know the interference that occurs because of their wavelength. And hopefully you see this in the final one, and then we better move on to some other things here. But what if I actually then had a double slit with the screen over here, with a lens? What would I have there? How would I do it? Well, hopefully you're thinking the same thing. You would get an image as the light went through that lens. Now I picked the convex lens, so the image could have been over here and been real images, or if it is under the focal length, the image could be back here and magnified. Why don't I draw it that way? But one option here is that the image of this one, and maybe I'll change colors to kind of indicate that, but if the focal length of this lens is, say, here, so there's focal length, then this lens would form an image of these two slits that would be virtual back here and magnified. And so these two slits, for anything on this side of the lens, would now maybe look like that, right? And this distance, which we might call P to begin with, how far is the object from the lens, after a little arithmetic, then give me the Q of how far then is the image from there.
Where's the light coming from?
Oh, light's coming from this side. So the light's coming from here, goes through the slits. Now as it goes through the slits, it hits the lens. The lens will then form an image. And so just like we saw in the chapter that you're doing now and wrapping it up, the image created from the first optical element now becomes the object for the second optical element. And in my case, my second optical element is not another lens or a mirror, but a screen and the interference that occurs because of those. So I would first start with this and know P. From that I would get Q. I would also use my magnification, because if this distance was the real physical distance D here, then this would be the magnification times D, wouldn't it? That would be the size of the slits. Right?
That's the Q from the slits, right?
No, Q is the distance measured from the lens. Yeah. So if I use the equation 1 over P plus 1 over Q equals 1 over F, the object distance is P, object to lens. Q is what I solved for, but remember Q is measured from where? The lens. Right?
Q's negative in that case?
Yeah, and then Q would have come out to be a negative number, right? Anytime my P is less than F, I get a negative Q. Had the lens been further out over here, then I would have formed a real image. Yeah. Okay, but this is a case of forming a virtual image with the lens. Well, now what do I have? Okay, I guess I would have expected d sine theta equals an integer number of wavelengths. I won't divide this one by n, because I'd have to be underwater for that, right? But also, didn't we argue that this equation was only valid if we had thin lenses, air on one side, air on the other? All right, so I've already convinced myself I've got to have air. If I'm going to use this equation, I've got air on both sides of my lens. So I don't need to really say there's an n. There's no way that one's underwater. Okay? Although I guess I could redo it and get an n here and then an n there. But anyways, but we use that equation for when we had air on both sides. But in this case, my d has now become magnification times d, right? Sine theta. And I have an integer number of wavelengths. And if I go ahead and replace sine theta with y over L, then I would say L is, I guess it was this original L that we had been talking about, how far are the slits from the screen, but I would have to add this much more to it, right? Which would really be Q minus P. So I guess down here would be my original L, and add to it a Q minus a P. And I suppose up here in the magnification, I could replace that with the Q over the P. So I got the P's over the Q's, the L's. Oh. You guys look less sure about yourself. It was easier before. Right? But I'll say it again. Not really doing anything different other than saying what happens to the light. It interferes.
Why does the L matter? It's not, I mean it's going over there. It's not even hitting the, I mean this wall may as well be at infinity.
Okay, at infinity in terms of the angle, yes. So when I stop at this line, L does not matter in terms of the angle.
Okay.
But L does matter in terms of distance on the screen. If the screen is close, the first order is here, and as the screen gets further away, y gets bigger and bigger.
Is that the center? Or what is that dot? The focal point?
That's the focal point from this lens.
So, okay, but, I mean, I guess I'm looking at the example where the lens is closer than the focal length, and it's reflected back. Or it's not reflected back, but it's, the image is sent back by the lens.
Okay, it's a virtual image, right?
So, wouldn't the L be P plus Q?
No. Okay. So, if you can imagine, okay, I think you're good with this. This is where the image would be. Fair enough?
Right.
Okay. Now, so what the whole idea of the image is to say that when you take the real object and the lens, the result of those two are the equivalent of the light being at the image. So if I could get rid of this opening and this lens, that is what the screen would see. The screen, the effect of the slit and the lens is what the image is. So all I have to do is now draw the image. And the image is what now becomes the object onto the screen. So as far as the screen is concerned, this is what the screen is observing. This is the effect of the double slit and the lens. And so that's why I first put the double slit in the lens and I find the image. Once I find the image, I don't have to think about that lens or that object anymore. I erase it from my mind because now this becomes the effect on that. So the image from the first lens now becomes the object for the second. And I'll say lens because we did that last chapter, but this is not a lens now. This is the screen.
So basically that image is right there.
So what I would see is a bright, dark fringe pattern, right? Bright, dark fringe pattern. As if the distance between the slits is a little bit bigger by a magnification. And as if the distance is a little bit bigger by whatever this image is added, and got to add on to that. Yeah.
So how did you find P initially?
Well, then that would have been given in the problem, that I had a double slit a certain distance apart and I put a convex lens 5 centimeters away. So they'd have to give me the lens, which would give me the focal length. They would have to give me P. From that I can get Q.
And L would be given.
And then you L, yeah.
So the things in red are not physically there.
Right, so the things in red are not physically there, exactly. They're the ones that have the appearance of being there. That's why we call them images. Yeah. Well, maybe I got too carried away. Those are some fun problems, but again, this is, our beginning optics. And the real thing is to just, hey, this is a double slit, and there's all kinds of combinations that we can have as we mix it up a little bit. But there's one thing we haven't quite said here, and it was your guys' question last time when we did this double slit. So let me even put the double slit back here, is we noticed something else. And you commented on this last time, that you don't just see a bright spot, dark spot. What about the stuff in between?
Ingredients.
And so I was starting to draw it here, and this is kind of like a graph, if you will, of if I were to plot the intensity on that screen. If my vertical axis represents intensity, I hesitate. I've been using Y for the distance on the screen, but that's horizontal, so should I? No, I'm going to leave it Y. And it's Y in this picture. And it's going to be a Y in the book's picture. But what I want you to see, both on the screen and in the calculations, is the in-between stuff. I thought your author did a good job here of showing the intensity pattern. Yeah, right here. Is he's trying to say, let's look at this a little closer. There is bright and then there's dark, but there's a transition from bright to dark.
So Q is a negative number, but in that last equation, it should say negative Q with a P.
Oh, fair enough here. Yes, when I did it, yeah, good point. When I did it here, when I calculated it here, I came up with a negative number Q, right? But when I treated it in this equation, I was treating it as geometry again.
At the beginning, too.
For the magnification. For the magnification.
Oh,
It should say negative Q because Q is a negative number.
But negative
yeah, and then I threw out the negative, so I actually treated it.
negative number, so it's positive.
But, well, let me just do that. Yeah, well, yeah, that's what it should look
But
like.
magnification is negative Q.
Yeah.
It's a negative Q, so it is
All right,
positive.
so do you want that?
No, it's negative, it is positive.
Okay,
We define Q as a
let's do that.
Q is negative.
we define Q as a negative number.
Because I treated all of this.
That'll work.
Yeah, I treated all of these as absolute values.
Sign conventions.
Yeah. Good point. In this part, I'm treating Q as a positive number. Yet in this one, I didn't. So I do need to be careful. All right. Well, the next part of this chapter is to go in between. Now that we've spent a long time looking at all these different combinations, let's look at this now. This is a graph or an experiment, which actually you will do in a couple of weeks too. You will measure the intensity. We've got this little probe, and you will put your little intensity probe right at the center, and then you'll move and you'll move and you'll move just a fraction of a millimeter, and you'll record the intensity. And of course, the true pattern's a bit more complicated. See, down the middle, it's really bright. Right here, this is the bright spot. That's our constructive. And when we get all the way over to here, we get complete destructive, right? But the truth is, there's light in between there. And so let's keep going and say, well, what happens in between complete constructive, complete destructive, complete constructive, complete destructive? And so there would be going from bright to dark, bright to dark, bright to dark. And of course, our argument was that you get the next bright spot when the distance between the two beams is one wavelength. And so your author down here on this scale is not plotting the y-axis, kind of like I have the y-axis here. But your author is plotting the path difference between them. And I don't know which is better. I really like that. What do I really see on the screen? So he's plotting the path difference so that he can emphasize that this is bright because there's one wavelength between the top beam and the bottom beam, or two wavelengths between the top beam and the bottom beam. And so that's great, but on the screen it's really a y-axis, but it's the same thing that you would see constructive, destructive, constructive. And there's my question right there. How far up or down on the screen do I have to go to get constructive and destructive? And what would be the intensity if I was part way between constructive and destructive? So let's work out some more math. Yeah.
Sorry to bring this up again, but that has to be a negative Q on the bottom. It cannot be absolute. Because if you had a Q on the on the right hand side, you'd have to say L minus Q minus P, which can't happen there.
Okay, I'm not okay, so this is L.
I'm saying if Q is on the right of the lens instead of on the left,
Yeah.
to find the actual effective distance, you'd have to say L minus Q minus P.
Oh yeah, I would have a different equation.
So to make this equation work for every problem,
Oh.
you should say negative q, negative p.
Okay, fair enough, fair enough. If it was on the other side, yes. But on this side,
Wouldn't we want to make it generic by putting it as negative q rather than absolute value of q?
yeah. Feel better if I did that? What would it, I guess it would be
Basically,
P minus Q, right?
L minus q plus p. L minus parentheses q plus p.
L minus, yeah, okay.
That should be a plus.
L,
Inside the parentheses.
yeah, yeah. I'm going to say yes. I think you're right here. Okay, but okay, fair enough. I'll agree. Definitely, it's not generically written. It was written only for the virtual case. If I'm going to use absolute
I feel
values.
like when we're talking about these, like you emphasize the fact that it's all sign conventions, and we need to be looking at the geometry and then thinking about what's positive and negative for that situation. So,
Oh.
like generic, we shouldn't be having generic from Latin.
But we can.
True.
Fair enough, but I was just trying to just do one special case that this is just the way of thinking. And if you happen to ever see that case again, great. If you don't, that's great. You just work out the geometry for that particular problem. Yeah, yeah. What I want to be generic was the optics that we did, and now the diffraction or the interference that we did, and then I can put those two together. Right? And also what I want to be generic is this next step here, right? What about the in-between cases? What is the intensity in between? And so, like I said, we've only done the easy part of the double slit, right? We have said where is it completely bright and where is it completely dark. We haven't asked the question, what about the intensity in between? But you can see in the diagram and you can see in the photograph and the plot there that it obviously has a bright, dark, bright, dark, bright, dark pattern. The question is, what kind of pattern is that? What shape does it? And fortunately, it's not too hard to work out. If I think about this double slit again, here's the one opening, here's the other opening, here's the screen. If I look at some position on the screen, then this wave is going to come in and hit that point, right? And our whole argument was that the second wave will also come in and hit that point, and that this second one will travel an extra distance of d sine theta. All right. So we kind of go back to the beginning of our optics, chapter 35, and say these are waves. And I should even ask, what's waving? It's been a while since we've asked that one. What are these waves made out of? Electric and magnetic fields, right? So if I were to draw the picture of this, it would be this. And this wave would be traveling along. Now that's only a two-dimensional picture because as I showed you before, and I'm not going to call it up again, but remember what was waving was the electric field and the magnetic field. So if the electric field is waving up and down, and the wave is traveling, in this case horizontally, which way is the magnetic field? Yeah, this way. That's why I'm not drawing it here on the board. So don't forget there is a magnetic one, but we don't even need to pay attention to that one because I'm just going to pay attention to the electric, and whatever happens with the electric also happens with the magnetic. So usually when we draw these, we just draw a wave and say, let's just look at the electrical part of it. So that's what I have here. Because I would say this is wave number 1. Now notice I put an E. Why? Electric field. Number 1. All right, so I'm going to put an E for electric field number 1. And, although it's been a while, way back we learned the equation for a wave traveling to the right. What was it? Look familiar? All right, so that's where I'm going to start. I do have a wave. This wave is traveling to the right. Now I'm missing a little piece here. What goes here? All right, so this is the amplitude of the wave. So again, I'm going to put an E. Why an E? Because this is an electric field. So this is an electromagnetic wave, right? And so E naught would be represented in this picture like this. There is E naught. And there's wave number 1. That's how I'd mathematically describe wave number 1. Let's talk about wave number 2 for a second. How would I mathematically describe wave number 2? Well, again, kind of assuming they're the same size of holes, and wouldn't I get the same amount of light through there? So I would say wave number 2 should have the same amplitude, right? It should be a wave also traveling to the right. But I'm going to make it slightly different. What's different about wave number 2 compared to wave number 1? Right, because it traveled a little bit further, there's going to be an added phase, right? And of course, as we've been talking about, if that added phase was 2 pi, you know, the equivalent distance of one wavelength, then these two waves would add up constructively. And when I added them together, I would get one number. But on the other hand, if that phase between them is pi, or pi, which is equivalent to a half a wavelength, then when I added these two waves together, they would cancel, right? But if I added them together with any phase, I would get everything in between. And so that's why I said this is the more generic case. When these two come together, we called that superpositioning a couple of months ago. We said, what is the total wave that hits the screen? That's wave 1 plus wave 2. The two come together. So what I want to do is add these two waves together and see what the total comes out to be. So the first wave is E naught sine kx minus omega t. The second wave is E naught sine kx minus omega t plus phi. Right? Those would be my two waves. And I don't know if you remember, but in chapter 18 we saw exactly the same thing. We had two waves, we added them together, we looked at the superpositioning of them. We used a nice trig identity. Maybe I should put it back here on the board here. What is sine A plus sine B?
Sine A.
All right. I think there's a 2 in there, isn't there? Sine of, and actually I'll put them in the order I want. I'll put the sine over here and the cosine over here.
The difference over 2 and then so.
Yeah, the sine has the 2 added together. The cosine has that difference. And I'm pretty sure it's a 2. I wrote it down. Yeah, good. All right, so there's my trig identity. So I'm going to take advantage of that. I'm going to apply that trig identity right here. So what will I get? Well, I'll start by just factoring out the E naught. So they each have an E naught. And I will start by calling this A and then this B. So what I have is the sine of A plus the sine of B. So I would have a 2 from my trig identity right here. And then I would have cosine. Cosine of what? Well, I got to subtract the 2.
Phi over 2.
Yeah, so when I subtract the 2, I get phi over 2. I guess actually I get a negative phi over 2, but cosine's an even function. So if you want to put the negative or not put the negative, it really doesn't matter. But I'll put the negative. And by even function, we mean cosine of x is the same as cosine of minus x. So even functions, as long as we realize they're even functions, we can just ignore the negatives. Obviously, in general, you can't just ignore the negatives. And what's the other one I get? Sine what? All right, kx minus omega t plus a phi over 2. Fair enough? But here's what I want to focus on. What I want to focus on then is, what would this tell me that I'm going to see on the screen? Or maybe I should focus on this first. If this had just been one beam, one laser beam. Yeah, question. Yes, it gets a lot of glare, huh? If this had been just one laser beam, you know, not going through two slits. If I remove this and just shine it on the screen, and I said, what are you going to see on the screen? Wouldn't it look like just this equation right here? So wouldn't it have the sine kx minus omega t? So I'm not going to pay much attention to this. Not to say it's not important. But what I am going to say here is, really, what would the effect of the two look like? In other words, that right there is your eyes seeing the electric field jiggling up and down 100 trillion times every second. And when you put the two beams together, it still jiggles up and down 100 trillion times every second. And it's the same frequency. So you're not going to see a change in color. Fair enough? And nobody expected that. I mean, I just shine it, and it was red when I got started, and I shined it to the two slits, and it's still red. Okay, so that part of it hasn't changed. So let me kind of ignore this for a moment so that I can focus on this stuff in front. What's this? Right, this would be the resulting amplitude. Again, had it been one beam, we would have said that's the amplitude. All right? And so if you look closely at this, this is saying that the amplitude would vary depending on what phi is. And what was phi again? The phase between that second beam. And so that's why, as I move along here, phi is changing, and so the intensity is changing. The amplitude of that wave is changing. And so it is going to go down. In fact, when would this be its biggest? Yeah, and so if I put the biggest here, that would happen when phi is equal to 0. And in fact, when phi equals to 0, I get an amplitude of 2a. I mean, I get an amplitude A of twice the electric field. Now, doesn't that kind of make sense of what we've been doing? We said that the waves would come together. Straight down the center would be phi equals to 0. Does that make sense? There's no phase difference between them. They've each traveled 8 million wavelengths, and they add up constructively. And so that's what this center one is representing. No phase between them. It's going to be very bright. But what happens when you move away from down the center? Phi changes. And as phi gets bigger and bigger and bigger, what happens to a cosine function? Less and less and less. And that's, again, what you're seeing in this graph. Starts off large, gets less, 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 less. Now eventually it'll go all the way to 0. When does it go to 0?
When the phase is pi over 2.
Yeah. And so you get a phase of pi. Because when phi is pi divided by 2, 90 degrees, cosine of 90 degrees is 0. Right? And so you get a 0 right here, which hopefully is perfect, because we were saying that the phase comes from this path difference. And the phase of pi would be representing a half a wavelength. And so when this distance is representing a half a wavelength, which on our wave means a phase of pi, the two waves are going to come together and cancel out. Exactly. And so now we have a relationship. We can get that equation, almost. One more step, yeah.
So on the wall, it gets dimmer as it gets from the center, but in the diagram, in the equation, it doesn't.
Fair enough. Remember what we are kind of avoiding at the beginning. Remember this thin one? And we put it in here. Oops. We put it in, and we said the thin one would make it spread out. If you look closely at the real picture compared to our math, let me make it just a little tighter. Does the intensity of the light spread out equally in all directions? Maybe I closed it too much. All right, I think I did. All right. There we go. So see how it spreads out? But does it spread out equally in all directions? No. But look at my math closely. What did my math kind of assume here? Same amplitude regardless of what direction it goes out. So, I guess what I'm really saying here is I have not done the whole story, right? I'm building up to the whole story. What I've done is the case where our animation made the light spread out equally in all directions. We still have to talk about why does the light spread out. Then we can figure out that it doesn't spread equally in all directions, and then we can add to this. And that's actually the first section of the next chapter. So they break it into two chapters, which is kind of weird, but they build up to it. So again, start with a double slit, why you get bright, dark, bright, dark. Now we'll add to that to say that the light spreads out equally in all directions, because a really small slit would be close to that. But the reality is they don't spread out in all directions, so we got to add one more step to it, which is what we'll do on Tuesday. Okay? So that's why our equation doesn't really match what you see on the wall completely. All right, so I'll keep going with this, but I think you get the idea that it's this phase which is connected to this path difference, which would explain why it goes bright, dark, bright, dark, bright, dark. Okay? And so, hate to erase that, but I guess I do have it over there, so I think I'll be okay. But now that I've got this wave, and this is what I would call the superpositioning of those two waves, this is really the amplitude. How do I go from amplitude to intensity? Now, again, I'll take us back a few chapters. What was the equation we had for the intensity of sound waves? Okay, fair enough. It was power over area. I agree. But we continued on and got that in relationship to amplitude. What did we get? Any of that look familiar? I know, it's been a while here. But again, as I said, I'm going to go back and remember some of our properties of waves. This was the intensity of sound wave. Now, we're not dealing with sound anymore, but we are dealing with waves. And so, back here, let's look at some of these. What did each of these stand for? I'll start with the rho. Density of the air, or whatever, water, if it was the sound waves. Okay, what was V? Velocity of those waves. What was the omega? Okay, frequency, angular frequency, to be a little more particular. Okay, and what's this? This is the one I want to focus on. Amplitude. It's not area, okay? This was amplitude squared. So what we saw back with sound waves was this, that the intensity was proportional to the square of the amplitude. Now, what I just did for you was a little bit of adding two waves with the trig identity, and I got the superpositioning, and this whole thing is the amplitude. Let me square it. So I claim for light waves that the amplitude would be proportional also to the amplitude squared. And so let me square this. If I square this, what do I get? 4 E naught squared cosine squared phi over 2. Right? Now I'm finally getting to answer this question. What's the shape of this? Cosine squared. Right? Do you see it now on the map? Goes up and down, up and down. And so if I wanted to know the intensity, say right in the center, what would I do? So at center. What's the intensity? What's phi right in the center? It's 0. So I would claim that the intensity would be related to that, right? And that's why I am going to write then.
What is the
Hang on, good question here, but I'm going to write the intensity then this way. If I, oh bummer, I think I just erased it. If I go right down the center, I will call that E naught. You see, down the center, I would have the 4 and the E naught squared and the sine kx minus omega t. What I wouldn't have is a phase. And so what I'm trying to say here is down the center will be our reference point. Down the center would be what I will call the I naught. What is the intensity down the center? As you get away from down the center, the intensity goes down. It goes down by a factor of cosine squared of phi. Phi being the phase between the two waves. Phi over 2, right? Now I gotta admit, phi is not a very good physical quantity to look at. It's the phase between the two waves. I would rather have distance on the screen, wouldn't I? So I'm not done here, but let's keep going and calculate this out. You do already know what we talked about, like, you know, what if phi is equal to 0? Well, then you get I naught. What if phi is equal to pi? Then you get 0. And so these are the special cases that we've been dealing with. Down the center, 0. 1 wavelength difference, 1.5 wavelength difference, 2 wavelength difference. And so let me do one more step. How could I change the phase of the wave into a distance? Well, maybe that would be useful to go back a picture. This, oh hey, here's that one we talked about. Yay! All right. But if I go back to the geometric picture that we started this class with right here, what I'm really saying is, how much phase do we have here? Right? That was the difference between these two beams. D sine theta is the actual path difference. So how is this phase phi related to a path difference? Well, what would you call this? This is that path difference divided by its wavelength, right? Isn't this how many wavelengths fit in that path difference, right? So I would say from here to here, if I take that distance and I divide it by the wavelength, I'm saying how many waves did I fit in there? Let's just say it came out to be 1 wave. What would the phase be? Yeah. 2 pi, right? 2 pi. That's a whole circle. That's a whole function. And so I claim that would be the mathematical connection between the geometry and the trigonometry. The trigonometry being how much of a phase of the wave. The geometry saying that phase comes from a path difference. And if you know that, we can now get rid of the phi. The phi, then, is 2 pi over lambda times the path difference. The path difference is d sine theta. Sine theta is pretty close to tangent theta, which is pretty close to y over L. And so there it is, my connection between the trigonometry and the geometry. How is the phase related? Well, makes sense. The phase would depend on how big is the wavelength compared to how far is it traveling. These factors are how far it travels. How far is the screen away? How far is the slit distance between them? How far up or down the screen have you gone? And so we get to the grand finale for today of this. What is the equation for the intensity on this double slit screen? I equals the intensity in the center cosine squared of yeah, remember I got to divide by 2, so that 2 is going to go away, and I get a pi, a d, a y, a lambda, and an L. And so now I have a much better equation than we started 2 hours ago. I can tell you the intensity anywhere on the screen. Not just where is it bright or dark, but where is it halfway between bright and dark? Where is it 30% dark? Where is it 70% dark? And I would make a plot then of the intensity versus y on the screen, and it would go bright, dark, bright, dark, bright, dark, bright, dark. And now, like I said, the question could say, go 3 centimeters on the screen, what's the intensity compared to the center? And you could say, oh, it's completely dark, or you could say, oh no, it's just as bright, and if it's any of those two, you're at your complete constructive or destructive. But it may be 50%, it may be 30%, it may be 70%, yeah. Only
have made that substitution and been able to find a specific M, like M1 or 2?
Hang on just a second, I'll answer that. All right, well, obviously we're done here for today. We got just a little bit more in the chapter to do, but I wanted to say for any of you who came in late, we did take a look at the test, and the test has moved 1 week back. Let's talk about Don and when he's going to do the review. But the good news is you won't be having the test next week. It'll be 2 weeks away. Yeah, so we got a little bit of time.